myself for 5 minutes of questions. I'd like to direct this to Dr. Chang-Diaz and Mr. Cassady and Dr. Pancotti, because I'd like for you to kind of delve into it a little bit more so for the benefit of all of us here. What capabilities, and let me just say this, I've had the privilege of touring and visiting two of you guys' facilities, and very, very interesting. What capabilities does your specific technology have that makes it unique? We'll start with you, Dr. Chang-Diaz.
For the Vasimer, there's certain features that are unique. One is that it can vary the thrust and the specific impulse of the rocket, keeping the power the same. Is essentially the same thing that you do when you shift gears in a car.
Right.
And if you drive a car like a race car driver, you step on the gas and you never let go, and all you do is shift gears. And so when you're climbing a steep hill, you would want more torque in your wheel, so you shift to higher thrust. And when you are speeding in flat terrain, such as interplanetary space, you would want to upshift to fifth and sixth gear, and then you will have a higher specific impulse. Still the same power, maximum, because you pay dearly for the power. And so it's important to have that feature. That's one. The other one, of course, is that when you're dealing with plasmas, you're talking about very hot substances, and you want to keep them off of the surrounding rocket casing. So you want to have magnetic nozzles, magnetic pipes that guide the plasma. The way you heat the plasma also is unique. We use electromagnetic waves. It's pretty much the same way you heat your coffee in a microwave oven. You don't touch it. You just launch these waves, and these waves wiggle the plasma, get it really hot. And we're talking about temperatures of the order of 2 to 3 million degrees. So these are some of the features, and that gives you a great deal of capability to open up in the technology. So just a summary.
Mr. Cassady.
I think the unique feature of our approach on the Next Step program is that we're building upon what we've already flown. Our device that runs at 100 kilowatts is what we call a nested hall thruster, and there's some description of it in the written testimony, but just for the group here today, we fly a 5 kilowatt hall thruster on the advanced DHF spacecraft now, as was mentioned earlier. It has a single annular region where the plasma is generated. The nested hall thruster takes that, adds a second ring outside, and then even a third ring. And each of those rings, you're running essentially the hall discharge. So we're able to take what we've known today, that we fly today, and scale it up simply without making it that much physically larger. We can scale it up to the much higher power. The other part of it is I would really like to delve into the system aspects. Because we're doing that approach, we're able to also deal with the power processing issues that we've learned a lot of lessons on in our flight experience. And not sure what's going on there.
Ignore that.
Ignore it. Okay, thank you. So the other half of the system, the thrusters are obviously a very important part, and they're the visible part that we all see. But the other half of the system is the power, and Franklin referred to that. We have to shepherd that power through very carefully, because wasted power is time to us. We need all the power we can get to keep that time down. So we're building, building blocks that we've learned from our flight experience into modular designs that we can scale up incrementally to these higher powers. And as Steve Jurczyk mentioned earlier, we also are working now on the 12.5 kilowatt hall thruster. It's another incremental step. So incrementalism is my I guess word that I would use.
Thank you very much. And Dr. Pancotti.
Thank you, Mr. Chairman. I think in my testimony I highlighted quite a bit about what we call ISRU, Institute Resource Utilization. And for me, when we're looking long-term towards sustainable infrastructures in space to become a spacefaring race or a multi-world species, advanced capabilities that will allow us to use the resources of our solar system will become vital. Just like today, if you wanted to drive across our country, you wouldn't fill up an 18-wheeler worth of gasoline to make it. You would stop along the way and refuel. And I feel like this is a very important aspect of building a sustainable infrastructure, to be able to go to Mars, scoop up atmosphere, and use that to propel your spacecraft to the next destination or to return home. ISRU has a large payoff for return missions, and also return missions from icy moons. So if we did want to go to far-off destinations, asteroids, or icy moon planets, we could take water, use that as propellant, and return very large samples to Earth. The other aspect I think that is fairly unique about FRC propulsion is the power. Not only is it scalable over a very, very large range of powers, like I indicated, for many generations of propulsion systems to come, we can use the same technology, but also the ability to vary that power over a mission. Because it's fixed energy, we can optimize an impulse for an exact energy condition, and then by changing how often we fire it, we optimize it, or we can use it over a very, very large range of powers within a single design.
Thank you very, very much. Now I'd like to recognize the ranking member of our committee, Mr. Barham.